So disabling interrupts is actually hardware. It's a hardware provided privileged instruction to temporarily defer delivery of an interrupt until it is safe to do so. So it's basically a hardware control that stops all different subsystems, all different hardware subsystems to have an interrupt. It can be in hardware and it can be in the actual operating system. So it varies between different architectures. Uh, you have the disable interrupt instruction that you can use when you're doing kernel programming to make sure that no interrupts occur in your code while your code is running. And if you disable interrupts, you have uh, an interrupt buffer where you basically buffer all interrupts. You save all interrupts in a buffer. Of course, this buffer is limited in size, so if you have multiple interrupts at the same times happening, these can be lost due to buffer size. Can give you an example. I will give you an example in a very short while. Once it is safe to re-enable interrupts, you enable interrupt instructions and you empty the interrupt buffer in order. So let me give you an example. Sometimes you have an interrupt happening. You actually do hit this multiple times. Uh, you have, for example, you're trying to open a really large file in Excel or in Word or in even in Unix or Linux, less and more, any of these programs that read the file. And while you're opening the file, you're trying to type. You now have an open call happening that is loading this file into memory, and every keystroke is actually an interrupt because every keystroke that sorry, every time you type a key, you're actually causing an interrupt. You might have experienced that. I have definitely experienced that some of these keystrokes, some of what I have wrote, some of the letters that I'm pretty sure that I have perhaps pressed on this letter does not appear on the screen once the file is open. Basically, what happened is that you have overflown the buffer interrupt. You only see the last three characters or something that you typed because your buffer interrupt has been overflown. So you never want your system to disable interrupts for too long, because if you do that, your system is pretty much non-functional. You cannot do anything. You cannot switch between different processes even, because switching between different applications, so you cannot, it will not happen because your timer interrupt will not kick in. So this is a very important thing to note when you're doing kernel programming in general. This is a case study of how x86 interrupts work. You basically save the current stack pointer, you save the current program counter, you save the current processor status word, which is basically the control bits, everything that is related to the processor. This is very x86 specific. x86 is basically the architecture of your Intel and your AMD processors that run on most computers, but not on mobile phones. You then switch to the kernel stack, you switch to the kernel mode, you vector through the interrupt table, and then your interrupt handler saves any remaining registers it might destroy. So for example, you do not save the floating point registers, as the kernel code should not be doing any floating point arithmetic. So this is just an example. Now we turn our attention to something that is called upcalls. And upcalls are basically the opposite of syscalls. Upcalls are when the operating system needs to inform the running application about an event. Something has happened, and you want the operating system to basically notify the application that this thing has happened. Uh, and this is also because sometimes we want operating system like functionality to be implemented in the application. So if you are, for example, doing parallel programming, if you have a supercomputer and you're managing the supercomputer, you're managing task placement on the different computers, and you're managing how much processing time each simulation or each supercomputing application takes. You want to be able to control the scheduling. You do not want the operating system to control your scheduling. So what typically happens is that you would use something like upcalls to decide which application to actually run. So if there is an interrupt. If there is a timer interrupt, it gives you an upcall, and then you do whatever you want. So in essence, upcalls are a way to notify user processes of some event that needs to be handled right away. So as I said, there are multiple reasons for using upcalls. These are some of them. Preemptive user level thread. You might want to multiplex the tasks yourself, run the different threads yourself, control which one runs now. You can have asynchronous input-output notification. You can basically allowing your application to decide what to do while waiting for I/O. You can have inter-process communication for a process to ping another process that there is something that needs immediate attention. You can have user-level exception handling, which is like the exceptions you get from your programming language. I mean, you get many of these exceptions that are actually implemented via upcalls. It's basically the operating system telling you that you're trying to do something illegal. And you have user level resource allocation policies. That is, for example, the Java garbage collector and the supercomputer. These are the upcalls in reality. You see that all Unix upcalls are on the first link, Windows upcalls are in the second link, and how Python handles upcalls is in the third link. So to give a concrete example of something that you are going to use in this course that is using upcalls, basically your virtual machines, the virtual machines that run on VirtualBox or whatever, they use upcalls because virtual machines are in essence user level application. Right, you're running VirtualBox, and VirtualBox is a user level application. So how do you, and then you're running inside that VirtualBox an operating system. How does it catch privileged instructions, interrupts, device I/O, and so on? So what happens is that it installs kernel drivers transparent to the host kernel. You have like your own kernel drivers, and you require administrator privileges, and this is something that we'll talk about a bit, but not now. And then it has its own interrupt table to redirect to the kernel virtual machine code. So you have everything is virtualized now. And then if there's an interrupt for a virtual machine, you have an upcall. So your way of communicating with the underlying system is using upcalls. So the upcalls are used in virtual machines to basically enable the virtual machine to get this feeling that it's running on real hardware.